This is going to be your cheat sheet for all the characteristics of various polynomial functions that you are going to be sketching. Let's start with our even degree n. I'm using n as a reference point here for the degree of our function because you could be exposed to a wide variety of degrees. First and foremost, the n behavior between power functions and polynomial functions is going to be the same. If you have a positive function, that means that your polynomial is going to be headed from quadrant 2 to quadrant 1. So it is going to look something like this. Okay? In our, if you have a negative leading coefficient, then you're going to be headed from quadrant 3 to quadrant 4. Something like that. You can always think of it as a parabola, just a more complex parabola. In terms of the number of x-intercepts that you're going to have, there's any range that hopefully you saw. The maximum number of x-intercepts is actually going to be equal to the degree of the polynomial. So we're just going to write n. So for example, if you have a degree 4 polynomial, the maximum number of x-intercepts will be 4. The minimum could be 0. It might be transformed with a vertical shift to be above or below the x-intercept, the x-axis, and therefore there might be no x-intercepts, and that's a-okay. In terms of the number of turning points, our maximum number of turning points is actually just going to be 1 less than the degree that we have. So if we have a degree 6, for example, then it would be 1 less, it would be 5. And the way we just write this is n minus 1. However, all even degree power and polynomial functions always have at least 1 turning point. Again, think of a parabola. That is your simplest version. It has 1 turning point. Our domain, so the horizontal sort of expands of our function here, is unrestricted. Whereas the range is restricted. And it's limited to either the max or the min value, depending on the function you have. There is some symmetry with our even degree functions. If you were dealing with a power function, okay, so that's the simplest form of your polynomial, there is always going to be line symmetry. Okay, which means that it's going to be symmetrical about a vertical line. Now, with our polynomial functions, sometimes there's going to be line symmetry, sometimes there's not. So I'm just going to write sometimes. It's always nice when there is because it makes sketching a little bit easier, but no promises. And that's it. That's everything you need to know about your even degree polynomials. Let's look at our odd degree polynomials now. Once again, I'm using n as a reference point for the degree that I'm working with. If it is a positive function, so there's a positive coefficient, then your function is going to be moving from Q3 to Q1, so something like that. And if it's got a negative coefficient, you're going to be going down, which means you're headed from Q2 to Q4. The number of x-intercepts, well, the maximum number is going to be the same as the degree. So if you have a degree 3, the maximum number of x-intercepts that you will have is 3. At least the minimum, you will always have 1. It is always going to cross the x-axis. If you just think about the nature even of a linear function, a y equals mx plus b, no matter how you shift that baby around, it's always going to hit the x-axis once. Turning points, so those turnarounds, the maximum number that you might have is just going to be 1 less than the degree, which is the same for your even degree polynomials, so that's nice and easy to remember. And in some of them, you won't have any turning points. Again, think of like your cubic or think of your linear. There's no turning points, it just continues on and on. So that might be the case for you. Both our domain and our range for odd degree, polynomial, and power functions are unrestricted. With our power functions, we have what's called point symmetry. Which is sort of like if you were to put a push pin or a thumbtack in one specific point on your graph, you could actually rotate like the top half of your graph. If you were to rotate it 180 degrees, then the graph would be symmetrical in the bottom half. So that's what's called point symmetry. Just sort of visualize with me, for example, like y equals x cubed. That's a great example of point symmetry. About the origin, the 0, 0, you would just rotate it around. Polynomials, similar to their even degrees, sometimes they've got point symmetry. Sometimes not. You never know what you're going to get. Okay, and this is a handy reference chart that just summarizes all of the key information that you need to know about characteristics of polynomial functions.